hydrogens or nitrogen groups on there, but as we're gonna learn in a second, we could make that into, is that the, I wanna call it a surfactant, but I'm not entirely sure if it's the right definition. We can turn it into an anion, and then sometimes that'll do it. We'll talk about it in a second. Liquid carboxylic acids they smell terrible, really awful. Like, you think vinegar smells bad? Mess with any other carboxylic acid and just keep it in the fume hood, and then like pay attention to whether you get it on your gloves, because if you get it on your gloves, you're gonna wanna just take off the glove in the fume hood, leave it in there, and put on a new glove. Like, yeah. These guys are acidic. There we go. These guys are in the Ka range of 10 to the negative fourth to 10 to the negative fifth. That means that their pKa's are somewhere around 4 to 5. Generally around 5, I want to say, but you can definitely put other things on there to make them slightly more acidic and get them into the 4 range. They are much more acidic than alcohols because of resonance. So, with an alcohol, if you deprotonate it, you've got nowhere for that to go, right? Because this guy has 4 bonds, and you can't break up the octet there, or you can't like expand the octet. That's what I mean. You can't expand the octet because we're in carbon. We're in like the first useful row, second row of the periodic table. But we have this, and all of a sudden we can do, that is supposed to be pointing at the bond, and that, and we can do, yeah, this is for resonance structures. So, question, if I have this carboxylic acid, actually, and I have this labeled with deuterium, or no wait, no, I don't want to do that, that's not what I meant. If we have this and I label the oxygen, I'm going to label this oxygen. So radioactively labeled, I want to say that's oxygen 18, but like, I don't remember. You can Google it and correct me if you want, or just know that that's the one that is a little bit radioactive. So if we do an isotope label on that one, and then we put this in water, are we going to end up with, let's see, let me erase this so I can draw our options. We're finished. We're going to end up with this still, or this, or a mixture of both, or are we going to end up with, I don't know, both of them labeled, or neither of them labeled? Well, not these, because I clearly drew them as an afterthought, right? So we're not actually, like, what happens to this in water? You've got an acidic hydrogen that's just, it's going to be able to come off. And when it comes off, you've got a resonance structure that basically makes both of these oxygens equivalent. So when you reprotonate it, you can protonate either one, and there's really no selectivity there. So you're going to end up basically having a mixture of your radioactively labeled oxygen and I guess probably not the desired outcome. I assume that's not what you wanted if you were radioactively labeling things. But yeah, that's what you're gonna get. Let's see. Oh, they're also much more acidic because, well, okay. More acidic is the same thing as the, I talk about HA and A minus, conjugate base acid. If I want to talk about which thing is more acidic, the easiest way to do that is to just look over here and find out which conjugate base is more stable. Because if this is more stable, this is more acidic, right? 1 to 1, like it's the definition of, it's basically the definition of acidic. You can take this off easier if this thing is pretty happy the way it is. So, yeah, when you're later looking at things, especially when they've got like, I don't know if you need to order things in order of like, which of these, they're all carboxylic acids and they all seem really similar, which of them are a stronger acid. Look for resonance, look for anything that will stabilize the conjugate base, that negative charge. So, the electron withdrawing ability of electronegative chlorine stabilizes the anionic charge through electron withdrawing. So this is more stable than that's more stable than this, right? Exact same thing, but over here, we've got a CH3 group, so we don't really have anything going on over here that's gonna help. Resonance is always way more important than sigma, like, polar bonds, right? Resonance trumps everything, but they both have resonance, they both have the same amount of resonance, so we're left to go, okay, well, is there anything over here that can help? These guys are slightly polar bonds, or these are polar bonds, that are gonna have more electron density down here, which means this guy is, has less of its bond electron density around it, and can kind of pull some of that negative charge away and stabilize that. Yeah? Okay. The formation of it is going to depend on the pH of the solution. So in Gen Chem you learned strong and weak acids, and you probably learned at least which one's vinegar? God, what is the name of it? Acetic acid. Acetic acid. And you learned acetic acid is a weak acid, right? All of the carboxylic acids are weak acids. And that's, if you look at the pKa table, you will see, you can tell from your pKa table because water's on, yeah, water's on here, right there. Water has a pKa of 15.7. There it is. So, if it's, oh, that's not the, no, hydronium. That's what I'm looking for, hydronium. It's not on here. Okay. I've got another pKa table with hydronium. I'm not can you deprotonate water, but comparing deprotonating, or comparing protonating water, right? Because if it is a stronger acid than hydronium, H3O+, then it's considered strong acid because all of it dissociates in water. And that's what Gen Chem is. It happens in water. There we go. So these guys are weak acids. Their pKa's are not, I want to say hydronium is like -1. Their pKa's are like 4 or 5. So not all of it's going to dissociate, and you're going to be able to push that equilibrium based on the pH. You get this concentration equal to this concentration when pH equals pKa. So if you know the pKa of your specific carboxylic acid, you put it in a buffer and adjust it so the pH is exactly the same as pKa, and you know this concentration is equal to this concentration. And acid-base chemistry is fast, right? Way faster than any other chemistry. Well, or what, any other? Okay. Any other chemistry that we're talking about that's semi-relevant to the conversation. I bet nuclear chemistry is probably way faster, but that doesn't matter. We're not talking about that. Acid-base chemistry is way faster than like substitution or nucleophilic attack. So if this one or this one is going to be reacting with something, then if you keep the pH at pKa, you're just going to, well, if you do a buffer, then that's going to help keep the pH at pKa. When you change the concentration of these, it'll just adjust for that so that your pH stays about the same. You're going to be ending up making more of whichever of these you're consuming in the reaction, right? Okay. Concentrations are equal at when pH equals pKa. Yeah. Otherwise, they hit an equilibrium. If you want to separate benzoic acid from benzyl alcohol, we talked about how. Cool. This is exactly how far I wanted to get, actually. We talked about how you can't, at some point, you've put enough carbons and stuff on there that you really are not going to be able to dissolve a carboxylic acid in water as well. So in this case, you can have diethyl ether, both of those dissolve in diethyl ether, and then you can do an aqueous extraction, but instead of an aqueous extraction, make the water kind of basic. Then it's going to deprotonate. Oh, this is to separate benzyl alcohol and benzoic acid, because benzoic acid can be deprotonated far more easily, right? So if you just, both of them are going to dissolve in ether, but if you deprotonate benzoic acid, then, well, it's an anion. Anions love to dissolve in water, so that goes down to our slightly basic water, and we can separate those two and have a nice liquid-liquid extraction. Distill ether. It's ether. I mean, you could distill it, or you can just sort of set it in the fume hood and wait 4.5 seconds because it's ether. Like, that stuff goes away like that. And so you're not gonna hold that under your nose, ever, in the lab. Whenever you have ether, you're being extra super careful, more careful than the other ones. Not because ether is like way more carcinogenic, because DCM is gonna be more carcinogenic, hexane's very carcinogenic, but there is ether is so volatile that it just evaporates really, really quickly, and you can get a lung full of it much faster than carrying any other solvent outside the fume hood. So be careful with it. Like, it used to be used to put people out, I don't know about unconscious, but out of it for dental procedures. And then if you want to get this back, rotovapping water is terrible, right? Because, like, God, water has such a high boiling point. I've done it before. It's awful. It's the worst thing in the world. So instead, you just acidify it after you separated these, and then it falls back out of solution. And you just filter it. There you go. So, we started chapter 17. Hell yes. I'm going to be very diligent about, I'm going to look through all of the slides we've got left for chapter 17 and decide what we can cut and what we can't, and we will finish chapter 17 tomorrow. If we don't, anything we don't cover in class will not be on your exam. And you'll know, well, you can double check what we cover in class because I always put post-lecture slides up. So, yes. I've decided that we're not going to do test corrections on your quizzes wanted to have your quizzes to return to you today, but I don't at the moment. But also, the turnaround time for that, I would rather you have the key to study from immediately after taking that, right? So, yeah, I'm gonna post the key for quiz 2, and then after you guys take your quiz, like, maybe like an hour later, depending. If somebody comes to hang out with me for extra time things, then I will post it, you know, a little bit later, since it's open internet, and if I post the key while they're working on it, but yeah, sorry, you guys can, it's 9:42, so you can, like, class is over, I'm just still talking, but.